Hi, in this lecture we discuss building uh, gates using diodes and BJTs. And one thing to note that the technologies and techniques discussed in this lecture are considered to be old. Newer technology using CMOS has been used in the last 3 to 4 decades, and they are the dominant in electronic industry. However, we want, from a completeness perspective, uh, discuss those gates that used to be constructed using diodes and BJTs. Okay, all right, so let's keep going here. Let's see if I like this and okay, so we'll talk about different techniques using diodes, and it's a good idea that you review logic gates, diodes from your digital logic class and electronics one class as well, um, because we're going to build on that knowledge. And if you have forgot some of those basics, please, it's good time now to go and do a quick review. However, for an inverter, for example, for an inverter, we know that the inverter input voltage will be reversed at the output voltage. So if you have, for instance, a low voltage here, you will have an output of a high voltage. And if the input is high voltage, you will have an output of a low voltage. Okay, so it's basically the reverse. Now, the AND gate, on the other hand, it will provide a high output if the two are inputs, or all the inputs, I should say, if more than two inputs. If all inputs are high, then you will have a high output. Otherwise, if one of the input is low voltage, you will get a low voltage at the output. So for instance, if this becomes low, then the output becomes a low as well. Okay, now it's important to note that here in this class we refer as low voltage, uh, equivalent somewhat to logic 0 in the digital logic class, and high voltage to somewhat equivalent to logic 1 in the digital class. Okay, and then we have the OR gate, um, in which the output here is low if all the inputs are low. If one of the inputs is high, right, and then the output will be high. And of course, if the two inputs are high, then the output is high. Okay, so these are some of the basics that I want you to in this course, what we do is that you have to most of the time what we are trying to we're trying to create a switch, and basically the switch here is this is where the transistor lives, whether it's a BJT technology or CMOS technology. This is where our the transistor is a switch which either connects you or disconnects you, and we will see later on how we use this switch. But one important concept that we need to keep with us is what we refer to as the characteristic curve. The characteristic or the transfer curve. The transfer characteristic curve. The transfer characteristic curve plots the output voltage of a system versus the input voltage, right? So anytime you have a system and you have some kind of input voltage and output voltage, you can always plot the transfer characteristic curve for the system. And what's the transfer characteristic curve? A transfer characteristic curve basically describes the behavior of the output, right? Right? As the input changes. You can see that the input here changes on this axis, and you can see what's the behavior of the output. Now obviously for an inverter, when the in this case we are plotting the transfer characteristic curve for an inverter. When the when the voltage is low, the input voltage, you have output voltage high. When the input voltage is high, you have the output voltage low. Okay, so important concept here we will use in this class is the transfer characteristic curve, which really depicts the or explains the behavior of the logic gate in terms of a curve. Okay, now another thing we need to keep in mind is the diode. The diode is our friend. We know that from our electronic class. Okay, so if I may use here eraser here quick, so to erase all of this. Um, so the diode basically here's oops, here's the diode. All right. Okay, so basically the diode, if you can establish a voltage of zero point 0.7 across it, then it short circuits. It short circuits these two points, this point to this point, with the with a droppage voltage of zero point 0.7. Okay. Now, if you cannot establish that differential voltage, then it acts as open circuit. It's basically disconnects the two nodes. Okay, so that's as we have studied. Now, typically we refer to this zero point 0.7 as the we refer to it as the VD on. So this is referred to as the VD on, which means when the diode conducts conducting. But if it is less than zero point 0.7, then our diode is off and it acts as an open circuit. A very important concept you have learned in your electronic class. Okay, now let's start with our first family of circuits. So let's start a new whiteboard here. Okay, so the very first, we are now starting the families of classes, and the very first family is referred to as the diode, diode, resistor, logic. Okay, so so this is the diode resistor logic, abbreviated as DRL. In this diode resistor logic, you see that the main important of this chapter is that we are trying to construct logic gates. So now we are constructing a logic gate using diodes and resistor, as you can see here. There's a diode. So in this case, we are constructing an AND gate. Okay, all right, an AND gate using what? We have two diodes, diode 1 and diode 2. And those diodes are connecting in this fashion, and we have here the first input and the second input of the AND gate. And then they are connected to a resistor 1, which is connected to a voltage here. Typically, we assume that this is 5 volt, okay? And the output is pulled from the node where the resistor and the diode meets as shown here. Okay, well, how this acts as a AND gate? Okay, how does it act? So let's assume, for example, we have 5 volt here and 5 volt here, and we'd like to refer to the 5 volt here as a high voltage and a high voltage. Okay, if you do such, here we cannot establish at this point more than 5 volt. Obviously, we are not establishing the zero point 0.7 across the diode. Obviously, the diode will be in an off state. Okay, all right. So if the diode is in off state, then the inputs are disconnected from this node. There is really this node, there is no current basically, so we assume that the current through the resistor is 0. Therefore, the differential voltage here through this resistor is 0, and therefore the V out equals 5 volt, which means it's a high voltage. Okay, okay, so you can see that this covers, in this case, so this table basically is giving me the different variation for the inputs and outputs. Now, okay, now Let's assume, let's see if I can erase this eraser. Okay, let's assume that a second case where, okay, let's assume one of the inputs here is low. So for example, let's assume, okay, let's change this to a pin here, back to a pin, okay, pin. Okay, so let's assume that here, this is a 0 volt, this is 5 volt, so basically this is low, and this VN2 high. We will assume one of the inputs is low. One. Let's see what happens when one of the inputs is low. And you can assume 0 volt, or if you want, let's assume, say for example, 0.5 volt, and that doesn't really matter. Okay. Now, so since this is low voltage, we'll see that there will be a conduction here, because there will be this node is more than the other node across the diode of zero point 0.7. It will conduct until there is a droppage of zero point 0.7 across the diode. We can go more. So this point here will have a voltage of 0.5 volt from the input plus 0 0.7, which is equals 1.2 volt. Okay, again, 0.5 plus zero point 0.7, that gives me the voltage at this node. Now, 1.2 is considered to be really a low voltage in terms of this technology. So you can see if one of the inputs is low, the output will be what? Will be low. Now, what's the current across this resistor? Across this resistor? Very simple. What we do is say 5 volt minus 1.2 volt divide by the resistor value. That will be the value of the current across the resistor. Okay? So this diode, resistor, logic, and gate behaves as such. When all the inputs are high, the output is high. When one of the inputs is low, the output will be low voltage. Now we can build another gate very similar to it, which is the an OR gate. An OR gate behaves in a very similar fashion. So let's see how we do this. Suppose, so you can see how the diodes are reversed here, and then we change the 5 volt to ground here. So that's two changes now, which makes this changes from an AND gate to an OR gate. Suppose I have both of these inputs are 0 volt, for example. Now 0 volt, we don't have enough voltage across the diode to turn them on, so they are off, and this node becomes a 0 volt, and the current across this resistor equals 0 volt, as 0 amp. Okay, and the differential voltage across the resistor will be 0. Okay, now, um, how about if we have one of the inputs, let's see if we change it to erase this a bit. So this is eraser, okay? So let's change one of the inputs. One of the inputs, let's change it uh, to a pin, to a high voltage. So this is, let's say for example, 5 volt, for example. And now I have enough differential voltage across this diode to turn it on. This diode is still, D2 is still off, but D1 is on. Now, if we turn it on, then we have a differential voltage of zero point 0.7, right? And this here, this node will be 5 minus zero point 0.7, which is equals to 4.3 volt. And now I can see there is a current now flows across this resistor, which is equals to 4.3 volt divided by the value of the resistor. Okay, so that now this when and we will consider this as a high voltage. When one of the inputs is high, this is low, this is high. When one of the input is high voltage, then the output is high. When the two inputs are low, then the output is low. Typical behavior of what gate? The OR gate. Okay? All right. So let's see. I think I covered all okay. So that's about the OR gate. So this family of diode resistor logic behaves as such, and then we will go to the next family. And before we go to the next family, we need to do a review of the BJT, the bipolar junction transistor that we studied in our electronic class. And we know for this device, the BJT, it has three terminals: the base, the collector, the emitter. And there are four modes. In fact, we use mostly three modes. So the four modes are the cutoff. All depends on the voltages of the VPE, right? If the VPE less than zero point 0.7, then this is the transistor is in off state and all the currents are zeros. If the VPE equal zero point 0.7, then it is the VPE is in zero point 0.7, then it is in forward active mode, and then the collector current is beta times the base current, and the emitter current is the addition of the base plus the collector. In the saturation mode, the VBE equals zero point 0.8. If the VBE equals zero point 0.8, okay, again here, then the important thing is that the differential voltage between the collector and the emitter equals zero point 0.2 volt. So it's almost a short circuit, not quite a short circuit, but almost a short circuit. We still have the emitter equals the base plus the collector, but here the collector is not equal beta but rather beta times the base times some diminishing factor here, okay, which reduces the overall collector current. Okay. Now in the inverse mode, the collector and the emitter reverse they are reversed. Okay. Okay, this is more elaborate diagram. Okay, all right. Okay. In the next few slides, I have some review slides. You can go over them. I'm not gonna go over those really. Just a refreshment from your electronic class. And what really I want to focus on here is the RTL circuit, and this will be the subject of next class and or next lecture. And thank you very much.